My name is James Goff. I work, it's a very, very lengthy title here, but basically the director of the Australia Pacific Tsunami Research Centre in the School of Biological, Earth and Environmental Sciences at the University of New South Wales. It's like one of those long Welsh place names, you know, when you join it all together. And I'm going to talk to you about, I suppose, what if we were complacent about tsunamis? I had to try and fit what if into the title because they told me I had to. So I suppose the complacency is not only the public, let's say, in general, but it's the scientists as well. And that's very important. We're all somewhat complacent about these things. And so it's important for us to get a bit of a lesson in what we know and what we don't know. So there'll be a bit of science in here, and then there'll be a bit of how the science has been used, and a lot of what we don't know, which might be worrying in the end. I'm not sure. We'll see. I like using this picture to start with. It's a very pretty place, Tomboling Bay. I don't know if anyone's ever been there. It's a very difficult place to get to because there's a certain group of people who don't like a certain group of people going there. It's right up near North Cape. It's one of the most northerly beaches of New Zealand. This is part of a tsunami deposit. It's also, for anyone archaeologically minded, showing a fair amount of reworked ovens and a few other things and middens in the picture. It rises up to 42 meters above sea level, and then it plunges down behind this dune into the wetland behind and sits there making a nice deposit. Very difficult place to get to, but absolutely stunning and scares the heck out of me. So, why a little complacency is dangerous and expensive. We're all pretty much familiar with the 2011 Tohoku-oki tsunami. 18,000 plus dead and missing. That represented 3 to 5% of Japan's GDP. That's an awful lot of GDP. That's a lot of money when you think about it. And of course, we can't really forget the Fukushima Daiichi nuclear power plant and the slight problem there was with that. You'll notice here, this is a picture of one of the waves coming over. You'll see a house there. Oh, I can't see it from here. Oh, there's a house there and a house there. That's those two. 2 years later. 2 years later. Done a great job at cleaning it up. That's it. Full stop. Great job at cleaning it up. No crops growing within the first 3 kilometers. This used to be a very high premium rice growing area, 2 crops a year. Nothing, it's too salty to grow, let alone the houses, etc., and the infrastructure, etc., and so on. So a very, very significant event there. To bring it sort of closer to us in the more recent past, I guess, what we call the 2009 South Pacific tsunami, which was Samoa. Nearly 150 people dead. People go, well, that's not many, but about 21% of Samoa's GDP for 4 years. That is a significant impact. Pacific Islands are unfortunately extraordinarily exposed to these kind of events. You have one island, it's got 360 degrees of coastline, all of it gets hit, and most of your infrastructure is normally on that coastline. So Pacific Islands in particular are very badly affected by these events. And let's not forget that New Zealand is a Pacific island, whether we want to believe that or not. Here's a little bit of science. The interesting thing is with the Japan tsunami, we all know how far the Japan tsunami went. That's the Apple, and here's the coastline in 2011, and that's how far it went inland, about 5 kilometers inland. Very, very destructive, very, very nasty, did an awful lot of damage. And the Japanese were caught completely off guard. Now, most of us in the game, no problem. Most of us in the game think of Japan as one of the most prepared, in fact, the most prepared country in the world. They know everything there is to know about tsunamis. They have a very well-educated public, and they know exactly what to do. Evacuation signs everywhere, drills every month. Absolutely fantastic place. They were completely and utterly caught out by this event. Hence, 18,500 people died. Actually, the best way of probably saying it is only 18,500 people died because they were so well prepared. The problem being, many died because they went to evacuation centers 3 or 4 stories high and drowned. So, and some of those evacuation centers were actually picked up and carried inland. So it was a fairly bad state of affairs. Why were they caught out? They have events. If you look in here, this is a sediment core taken from the surface going downwards. That's the previous event. They call it the Jogan in 869 AD. For them, historical. For us, well into prehistory and beyond. There's the previous one before that, and there's the one before that, and there's one down here too. So they had lots of events, lots of things to look at, lots of things to study. They knew about all of these before 2011. And this is the orange. So I'm comparing an apple with an orange. There's the Jogan shoreline from 869. And there are what the scientists said was the limit of the Jogan tsunami. Much smaller distance. That's only maybe a couple of kilometers, maybe 3 at the most. This is 5 kilometers distance. This they put down to a magnitude 8.4 earthquake in this area, and this one was a magnitude 9 in that particular area there as well. Huge difference in the size of the earthquake, huge difference in the size of the tsunami. Wrong. The reason why they've been getting those things wrong, and the reason why a lot of us have been incredibly surprised by the fact that they were caught out so much, is because, unfortunately, the traditional techniques of doing geology, which is largely what I do, are killing us. We're not understanding how big tsunamis can be. And to put that into context, here's the sea, here's the maximum point inland, and there's the tsunami heading off from left to right. It starts off with a lot of sand. This is all sand, that nice color there. And around about 2.6 kilometers, the sand runs out. Up until just after 2011, the only thing that the researchers were ever looking at was sand. The tsunami sand. Everyone thinks of a tsunami as being sand or something bigger. It's a very high energy event. And then after 2.6 kilometers, it turns to mainly mud. And the mud runs out at 4.5 kilometers. It is still damaging things at 4.5 kilometers. It goes further inland, it goes to 4.85 kilometers where the water runs out. Right here, a gripping picture of a paddy field about to be planted up. Not very exciting. Now, if you look at the mud, which, interestingly, when we first found a paleo-tsunami, in other words, prehistoric event, in this country, back in 1994, it was in Abel Tasman National Park. It was 3.85 kilometers inland, and it was mud. We didn't know it was a tsunami. We did a lot of work trying to figure out what it was, and we ended up working out it was a tsunami. So we were always studying the mud as well as the sand. We then went out into the big wide world and started talking to other people, and were scratching our heads because they were all looking at the sand and not the mud. Slightly confusing. So after 2011, they suddenly realized, and a lot of our colleagues suddenly realized, that the devil is in the detail. It's in the mud and the sand, and when you get beyond the mud, you get into geochemistry. That is salt water, that is not. That is exactly where the tsunami stopped, and the geochemistry tells you. They didn't know that. No one else found that, except for our team of people. I should point out, by the way, that I arrived in New Zealand in 1993. I left New Zealand in 2008 to go across the ditch to earn Australian money, where they pay me a lot more and I can bring it back to this country when I retire, which is great. I do a lot of work in New Zealand still. Being in Australia gives me the money to do the work that needs to be done in New Zealand. And that for me is extremely important. So, the mud and the geochemistry is essentially a New Zealand idea. Not a lot of other people ever thought of that. Some people did. In fact, some Japanese people did, but they were largely ignored. All right, a little bit of geology. Tsunami hazard assessments. This is what you get told. In other words, a whole bunch of scientists go out, do some studying tsunamis, bit of geology, bit of fancy modeling using mathematics and things, and we end up telling you, oh, you're going to get a tsunami this big, let's say, on Brighton Spit or something like that. Now, all assessments underestimate the hazard, and therefore they underestimate the risk that you're exposed to. I will probably get shot down in flames by some colleagues, but it's entirely true, and I have arguments about this all the time, largely because the models that we use, which look very pretty, and I'll show you one in a few minutes, they use what are called simplified subduction zone events. A subduction zone that's where a lot of the big tsunamis come from. You basically have a fault line, think of whatever fault line you like, under the water, and it's where one plate, like in these two pictures at the bottom, one plate is actually being subducted, that's why it's called a subduction zone, beneath another one. And that other one is being pulled down, pulled down, pulled down, and suddenly it says to hell with this and bounces back up again. When it bounces back up again, that's the tsunami. And it's happening along hundreds of kilometers of the sea floor, because this has to happen underwater to generate a tsunami. happens under hundreds of kilometers, and you get this massive great wave coming in and inundating. That's a subduction zone event. They don't all, what we do when we model them is we say, okay, well, we'll assume it went up 10 meters all along that length. And that's what we call a simple subduction zone model. Unfortunately, nothing's ever simple in nature. Some bits go up 10 meters, some bits go up 20, another bit might go up 50, one bit might go up 1. But just to make it easy, we do it as a simple one. That's the problem. It doesn't work that well. It's also a very bad assumption that subduction zones are the only thing that generate tsunamis, and that's what a lot of this presentation will be about. 14% of all tsunamis greater than a meter since 1977 have been generated by non-subduction zone ones. That's where, for example, that's that little green bit where the fault's just going like this. It's what they call a strike-slip fault. And what happens, there are two things that happen with the strike-slip fault. First, Mother Nature isn't very kind like this. It doesn't always go just like this. They are predominantly strike-slip. So they go like this, but they also have a little up component in them as well. Some do, not all of them. Like the Alpine Fault, we all know that one. That is predominantly strike-slip. We'll come back to the Alpine Fault a bit later on. Predominantly, so that does generate tsunamis where it goes offshore south of Milford Sound. But also, if you imagine there's a block here sliding, this block here is actually, if you imagine that's the end, it's pushing. And that's actually pushing a wall of water along with it, so that actually does generate a smallish tsunami as well. So, not only these ones can generate them, but these guys can too. Oh dear, we don't include those in the model. Annoying. Landslides, into the water, under the water. They generate tsunamis too. Difficult to model though. So you don't. Fair enough. And volcanoes. They can be very annoying. Sometimes they blow up underwater, generates a tsunami. Sometimes they blow up above the water and under the water, and that's very messy, and they generate tsunamis. Sometimes lots of things fall off the side of them. Pyroclastic flows, big hot bubbling mass of hell falling into the water, that generates a tsunami. But also, volcanoes are big steep things like this, and large bits fall off the side from time to time. They're called flank collapses, or just imagine them as a submarine landslide or something like that. They generate tsunamis. Gosh, we're getting a whole lot of generating of tsunamis without much in the model at the moment, but there you go. Every now and again, though, there is someone who thinks slightly outside of the square, and they say, well, look, we're getting some really big tsunamis being generated using this fairly simple model, but how well does that match up with... It's normally matched up with historically documented accounts. And that's great, except in New Zealand, history of tsunamis is about 200 years old, which, to be honest, to try and understand what a 1 to 500 year event might be, doesn't really give you much to play with. For example, when was the last tsunami in New Zealand that went 20 meters above sea level? The answer to that is never in the historic record. In the prehistoric record, lots of times, thank you very much. So just using the historical record is a little difficult. The problem is that incorporating all of that geological information into a mathematical model is a little difficult. That's where the problems arise. So not only are the geologists not necessarily getting it right, the modelers can't actually do much with it. So you end up with this, we're fudging it quite well. There are a couple of places, I think there are 3 cases I can think of, where models have been matched up with geological data. I almost wanted to have a sort of trumpet there or something, but Seaside, Oregon, they have worked out the 1 in 500 year tsunami based upon a 6,000 year record of previous events. We'll come back to that later. That's an excellent example of what can be done using the two. But let's have a look at hazard assessments in action, so to speak, what these things do. So we produce these little simple models. We look at all the subduction zones. We're going to look at the Pacific here. It's that lovely place right up there. There's the Pacific. This is the Pacific Ring of Fire, which is pretty much marked around the edge by subduction zones, pretty much. Not all the place, but pretty much everywhere. And then we produce these as models, and you fire in these tsunamis that they generate. So the red lines are pretty high tsunami. The yellow bits, it's not quite so bad. And then it kind of filters into this lighter coloured yellow, and that doesn't get affected at all in there by the look of it. And those are the kind of things you can do. Looks pretty, doesn't it? It's great. And that's it. You then go and you look at every single island around the Pacific, and you work out exactly how bad any tsunami is going to be in any particular island. And that's what these little guys are here. I'll come back to a bigger picture, so you don't need to squint. I'll come back to a bigger picture. These ones show, in fact, American Samoa, the Cook Islands, Fiji, and French Polynesia. I thought I'd get a little bit of a flavour in there of the Pacific. But if we just focus in on the Cook Islands, since they're loosely connected with us, so it's always nice to think about something moderately local. Here are the Cook Islands. And the Cook Islands are that little X in general, marks the spot in the model. And you look at these are all of the, it's all been run, these models have been run, firing in from these subduction zones. And all these little bar charts show how high the wave is going to be in the Cook Islands if it comes from, let's say, here, or it comes from here, it comes from here. And there's this massive great one sitting right there next door to the Cook Islands. That basically says this is the Tonga-Kermadec Trench, which runs from pretty much, let's say, East Cape northwards to Samoa, that kind of area. And it says, okay, well, the Tonga-Kermadec Trench is the most significant source. Yes, it is, correct. I believe that one. And depending on whether we're in the north part of the Cook Islands or the south, once every 2,000 years, you can expect a maximum amplitude, that's from the height of the wave right to the trough, of anywhere between about 1.7 and 2.8 meters. No problem at all. 2.8 meters, easy. I love that, that's great. I'd live in the Cook Islands for that. So, let's go to the southern Cook Islands. Minaya, lovely place, I recommend visiting it. How come in 2010 they had a 12-meter tsunami? Well, a tsunami that went up to 12 meters above sea level. It's only meant to be 2.8 there. Not only that, they've had 5 previous events in the last 30 years that have gone up to that height, between 10 and 12 meters above sea level. And not only that, but the neighboring islands of Moke and Attu have had at least 3 events each in the last 30 years that have gone up to 10 to 12 meters above sea level. There's no data missing, so who really cares? Well, I care. The hazard assessment's wrong. They've had, how many is that? That's 6. That's 11 tsunamis in 30 years in that neck of the woods, all of which have been significantly bigger than the hazard assessment says they're going to be. That's not a good start. It's not a very good look. So the question is, how can we improve our knowledge? This is the scientists improving the knowledge, but equally, the people we're telling, we would like them to know what they're getting is the right story, or at least the best we can do so far. First thing, can tsunami hazard assessments be improved using the existing knowledge, the knowledge we already have? And then, can we actually improve that knowledge as well? That's really what we're saying. And then we can avoid black swans. That doesn't mean when you're walking across Hagley Park, you're going to see a swan and walk around it. It's an economic term. It basically means an event that comes out of left field. Completely unexpected. You don't know this is going to happen. And 2 classic examples of black swans. This is the 2011 tsunami, a beautiful model that's been generated. And this was the 2004 Indian Ocean tsunami. Beautiful, lovely colours. They look lovely. These, to try and make them sound even sexier, these little red bits are now called the fingers of death. Yeah, it's actually, unfortunately, quite true. In this instance, incidentally, the 2011 Japan tsunami it actually wiped out 250 houses in Chile, and it went about 200 meters inland in Chile. So it went all the way across the Pacific and hit Chile. So it was a genuine Pacific-wide event, that one. Okay, so how do we improve things? Put simply, we need new glasses. You know, you go to every time, as you get older, you go to the optician, you need to get new glasses because your eyes are getting worse. That's the problem. We're not seeing properly. We actually need to go out there and use every single thing we have available to us to understand what's going on. And one of the big problems with tsunami hazard assessments is that majority of the models that are done by seismologists. Seismologists study earthquakes, subduction zones. They're the ones that cause most of the tsunamis, so therefore seismologists do the work. Unfortunately, they don't do tsunamis, they do earthquakes. And I have a continual ongoing fight about this because it's easy to do the earthquake stuff. It's much harder to do the submarine landslides and the volcanoes and so on. And if we don't do them, we're not getting the story right. So as long as it continues to be dominated by people who do a lot of earthquakes, we're in trouble. We will continue to underestimate the problem. Once we recognize that issue, we can move forwards, and that's fine. I just love this little cartoon of these guys looking at the fault line as the asteroid's about to take them out. But they go, oh, and incidentally, I don't know if you can read that. Oh, you can't. Hang on. It says, The data don't predict a tsunami with absolute certainty. I still say we wait. Yeah. That's really not very focused, is it? Oh, dear. Oh, well. So, recognising the issues, I'm going to take you through some of the sources. And some of them really don't necessarily need to be in your average run-of-the-mill tsunami hazard assessment, but they're sources, and it's important to at least be aware of them in the back of your mind. So, with that, let's start with Bruce Willis, Armageddon, and asteroids. Well, to generate a tsunami, they obviously have to fall into the sea. That's the first priority of those things. And there are several different sizes that we think about. There's 5 to 10 meter diameter ones. They happen annually. They're around about the same size as the Hiroshima bomb, but they normally explode in the atmosphere, so we don't worry about those. Phew. Then there's the 50 plus meter diameter ones, getting a bit bigger. They happen about every 100 to 1,000 years, those kind of things. Tunguska in Siberia fell on land. Well, it actually exploded just above the surface, but that's sufficient to obliterate a large metropolitan area like Christchurch, easily done. And a little bit of, can you read that one? I love this. The ship Strathblane, bound from Honolulu, has been lost at sea. She was struck by an asteroid and sank. Wow, can you imagine the luck of that? There you are on your ship, going along merrily and suddenly, wham, out of space. Well, that was it. Yeah. Actually, never believe everything you read in the newspapers. Hey, we've heard that one before. Because, in fact, what happened is this ship was crossing the bar, a bit like you do at Greymouth or something like that, and it sank, and it was at a place called Asteron. Oh dear. I got really excited by that because I'm doing a database of tsunamis. I got really excited, and then I somewhat disappointed. And then we get to some slightly bigger ones. 600 meters to 5 kilometers. This is getting pretty big. They happen about every 100,000 to 1 million years. But again, they have to fall in the deep ocean. It's really difficult to find these things in the deep ocean because they don't leave a crater unless they're really big. And so we only know of one deep ocean impact, and that was the El Tanin, 2.5 million years ago. This is the kind of, not quite, well, it probably is the Bruce Willis event, I guess. It'll wipe out at least 25% of the global population, starvation, famine, da-di-da-di-da, the usual things. I'm just going to see if I just want to show you an animation of this. You've got a kind of a still of it there, but I just want to see if it works. Scientists and technology. Okay, and I'll explain a couple of things as we go along. It says it's a simulation of a 1 kilometer diameter event. There it is, just off to the southwest of Chile. And then you get some colors here. Look at the reds. Remember, that's about 10 meters, okay, something like that. And here we go in a minute. It's going to tell us some boring numbers in a second. There we go. Oh, that was New Zealand. That was Australia. Oh, good grief, that was Alaska. That's pretty cool. I like that. Excellent. Downside with that, this is back to models again. That was modeling a 1 kilometer diameter asteroid. The reason why because in fact the El Tanin was about 4 kilometers in diameter, so that's not really what happened. But the problem is models get unstable when you start working with these things over about 1 kilometer in diameter, so actually it's a lot worse than that picture showed, just to get you comfortable and thinking about these things. But if one of those happens, don't worry, it's only going to get worse. The 10 plus kilometer ones, these are the Dinosaur Killers. We don't really want to go there. We know most of the ones that are in the near-Earth orbit at the moment. So apparently, according to the experts who study these things, they're unlikely to happen for at least a century. Gulp. So really, the ones that are probably the most concerned are probably around about the El Tanin type, because they occur quite often. They can be really, really nasty and horrible. The worst thing is that there's hundreds to thousands of those around our neck of the woods we don't know about. Well, okay. But that's asteroids. We can't really do much. I put this bit in really because it's important to know about asteroids, but to try and do a tsunami hazard assessment taking into account asteroids is just ridiculous. You can't do it. But it's always nice to know these kind of figures and numbers. Oh, there's a few of those wandering around out there. Good. Great. I'll have another beer. Okay, so earthquakes. Let's get down to something a little bit more manageable. All sorts of earthquakes. And a couple of very well-known professors, guys called Kenji Satake and Brian Atwater, sort of gods of both earthquakes, and the second guy is pretty much a god of tsunamis as well. They made an interesting statement, which sounds a bit scientific, but I'll explain it. Simple geophysical hypotheses about maximum earthquake size at subduction zones. and about patterns of earthquake recurrence appear to be of limited value in the long-term forecasting of the time and size of great subduction zone earthquakes. Basically what it says is we don't really know too much about how big and how often these things happen. That's loosely put. And they say we need to search for evidence of giant earthquakes unknown in the historic record. I totally agree. And remembering that these things, when they go, they also generate tsunamis, I would also add tsunamis to that picture as well. So these guys, who are gods of the field, are saying, actually, you know what, we don't know much, but we're trying. Putting that in a bit of a context, Japan, 2011, that was a kind of that was the first example I gave you. If you go back to Chile, and this is a picture of tsunami deposits in a wetland in Chile, 1960. Anyone here remember 1960 tsunami? Yes, great. It's always good to have some people here who remember it. Unfortunately, I wasn't too big at the time, so I don't remember it that well. But it's an important one to remember because it's probably the last reasonably decent one we had. That sounds horrible. Sorry, I shouldn't say it like that. Probably the last one that was of a reasonable size that struck New Zealand, 1960. But when you look through the record, here we have in Chile, the one before that was 1575. Historical for them, not for us. It's interesting because if you look at the figures down here, 9.5 is that one. There's the 9.5 question mark. The question mark is because they think it was actually bigger than 9.5 is the biggest earthquake in historic time. But actually, although historically they think the 1575 was bigger, maybe a 9.6 or a 9.7, which means that the tsunami here would have been bigger. The comforting thing, if there is anything with that, is that south-central Chile isn't the worst place for us to get tsunamis from. It's northern Chile, which was 1868, and that was much nastier than 1960. So, but they have an historical record that's longer than ours. Do we use it? No. But also, what about this one? And there's a little one in here, little line going, stop shaking, little line going through there. There's one here, and there's a big one here as well. These are prehistoric ones. These are ones where people like me go out and play in the mud, dig holes, like a little kid in a sandpit. Those are the things that we study, because unless we understand how many of these there have been, going back in time, we really can't tell you how often they happen and how big they're going to be. So this is what I go out and do, and we're the ones who make a lot of mistakes trying to figure out what on earth these things are. So if we come to New Zealand, because I love New Zealand, and we look at the Tonga-Kermadec Trench, which is this guy here, that was the one that did the damage for the Cook Islands. And here's a model of it here showing waves flying off in all directions and Northland being a strange colour because it gets hit quite hard. And a paper came out, this is based on a paper that came out in 2011, comparison of geological data assigned to a tsunami in approximately 1450 AD shows an intriguing similarity in distribution and scale to our model output. I put that in italics. But they also said when we consider that we consider that such a scenario, which is a magnitude 9.4, which is very big on the Tonga-Kermadec, we think it's unlikely to ever occur. Hang on a second. They're comparing it with geological data, but the model can't be right, can it? Because it can't be that big, even if we got geological evidence for it, interestingly. 10 years earlier, I wrote a paper that said paleotsunami research points towards a magnitude 9.3 plus event on the Tonga-Kermadec Trench in the 15th century. Completely ignored, that's great, thank you very much. Which comes with a lovely piece of deja vu in it, because in 2008, the Tokyo Electric Power Company brushed aside geological concerns that a bigger tsunami was possible than they planned for at the Fukushima Daiichi power plant. Boy, do we learn our lessons, eh? Are we going to learn them here, is the question. Non-subduction zones, those are the ones that don't go like this, they mainly go like that or whatever. Predominantly strike slip. That's the Alpine Fault. In 1717 or thereabouts, give or take a year or 10, it moved about 15 meters that way and about 5 meters that way. That way's the bit that worries me, because when you get just south of, it's going to be in here somewhere, it's just south of Milford Sound, it goes underwater. It becomes submarine. And so therefore it did and it will generate tsunamis. It goes a little bit further and it gets very complicated and messy around here, and then it becomes a a subduction zone again. This is called the Puisaga subduction zone. This area around here is probably responsible for generating what is around about our first historically documented event in 1826. So we've even had one from that neck of the woods in historic time just. And it'll be coming to my batch anytime soon. Can't wait. If you thought that was bad, sorry, we're not going for doom and gloom all the time, I promise. Let's talk about volcanoes, eruptions, those flank collapse things, and these pyroclastic flows, all hell dribbling into the water. I thought I'd give you Indonesia, because Australia's in the way, and that's always good, you know. Couldn't happen to a nicer place. It's an interesting spot. They have a lot of volcanoes, and they have an annoying tendency of blowing up every now and again. Most of us know Krakatau, or as some people know it as Krakatoa, which was a misspelling that was done by Reuters at the time, and has stuck with us for years. That blew up in 1883, killed 30,000 people, and it was at least 30 meters high, something like that, a horrible tsunami. And the tsunami around New Zealand was around about 2 meters high. I think it was 6 feet in the old money, which was not too bad, but it came from a long way. You know, you've got to think about it. It came from Krakatoa's there. It's got to kind of go down here, past Western Australia, hang a left, come along here, and then up again, and you hit New Zealand. So it did a good job at being 2 meters high still. That was pretty bad. Now, of course, dealing with prehistory, Kauai, which is much closer to home, that little guy there in the middle of Vanuatu, blew up in 1452, 1453. That was huge. It wasn't big, it was huge. 10 times the size of Krakatoa, and closer to us. Oh dear. Oh, and let's not forget there's actually the thing you find generally associated with subduction zones, just behind them somewhere usually, are volcanoes. And we have plenty of those wandering merrily up from the Bay of Plenty up through here. So Niwa goes out with a boat every now and again, finds a few more volcanoes, and we go, oh dear, there we go. Another one exploding here. So we have a few volcanoes close to home. This, incidentally, is an estimate of the range of the tsunami generated by that event. It is published, but I now don't believe it. So, and since I wrote it, I'll come back and explain it later. Other volcanic-related things, and we need to put this in a context, several bits of context, actually. Volcanic-related tsunamis only make up about 10% of all historical events. So how bad can they be? Well, there's two issues there. One is all historical events are all historically documented events. The historical record is incomplete. You can imagine standing next to Kauai when it blows up, writing this, you know. Oh, well, that's gone. So not surprisingly, we don't actually have... We know it was a very big event because we record it in the ice cores. The ash cloud is recorded in the ice cores in both the Arctic and the Antarctic. Big event. So, going on. There's an almost invisible threat that comes down to volcanoes, and it's actually quite worrying, particularly when we live around the Pacific. The Pacific Ocean has over 10,000 seamounts. Seamounts are like, if you want trainee Pacific islands, they're growing upwards. They're volcanoes, essentially, that are under the surface of the water. They're either growing up or they're collapsing or they kind of didn't make it and stopped halfway. Places like Hawaii are actually seamounts that made it to the surface, and you've just got a little peak of the volcano just above. So the big island is kind of just like the very top of the volcano. And there's about 4 kilometers of it underwater, waiting to slide into the sea at any moment. And they do that. You get giant flank collapses, submarine landslides that occur off these things. And I'm trying to think, I said hundreds to thousands of cubic kilometers. Great, that's helpful. Imagine Hagley Park, which is, it's slightly bigger than that, but let's say it's about 1 kilometer by 1 kilometer. And then you add 1 kilometer on top of that. That's 1 cubic kilometer. There you go. So Hagley Park, kilometer deep. Now, say you've got 100 of those or you've got 1,000 of those. That's the kind of size of event we're talking about. They're fairly large events. Not very nice. Hawaii's had a few of them. The new Anu event is northeast of Oahu, so Hawaii 5.0 would not be running that day. It would be off. That was somewhere between 2,000 and 3,000 cubic kilometers, so between 2,000 and 3,000 Hagley Parks falling into the sea at one time. A more famous one, which is off the Big Island, called the Alika Slides. There's several of them. One which was 600 cubic kilometers. It only happened about 250,000 years ago, so who cares? The tsunami generator for that went up to at least 800 meters above sea level. Yeah, that's great. That's a biggie. But wait, there's more. I always wanted to say that. Smaller seamounts and atolls, and atoll-like islands, which are basically seamounts on steroids who've made it above the sea surface. They regularly have slope failures of kind of 20 to 50 Hagley Parks. They're very common. And we've got well over 20,000 of those in the Pacific. So there's a lot of them. Don't forget the 10,000 seamounts as well. Putting that in a context, and it's very important to understand the context, a small one, which is like 1 Hagley Park, a submarine landslide like that can generate large local tsunamis that can throw things like this. There's a person. 20 meters above sea level. Imagine that on your front doorstep when you get up in the morning. You know. But then moderate to large ones, the kind of 10 to 100 times size of Hagley Park, they're responsible for some of the largest known tsunamis in historic time. One particularly good example is this one in Papua New Guinea. There's a bucket sitting in a tree there. I won't go into great details explaining that, but that bucket doesn't actually tell you how high the tsunami was. But the tsunami did get up to, in some places there, about 15 meters and killed thousands of people. And that was 1998. So these things are kind of like the silent killers that we don't know too much about. Very difficult to model because ultimately, well, where do you model it? Because until it's happened, oh, that's where the slide was. You know, with a subduction zone, we know where they are. With a submarine landslide, well, which island do I pick? Which angle do I pick on the island? It's very difficult. And then actually modeling it as well is tough too. Okay, so there's lots of seamounts and atolls, can't be that bad. Remember, they're only about 10% of all tsunamis ever recorded historically. Charles Darwin, bless his cotton socks, good scientist, he would beg to differ. On the left is Charles Darwin's theory of atoll formation, a brilliant piece of work. Basically, here's your volcano, it grows up, gets to the surface, then it sinks down again, and then you get left with this lovely little atoll that looks like this. Very pretty. Great rings of coral, he called them. Unfortunately, if you cruise around Google one time around the Pacific and have a look at these atolls that we have, 95% of them look like this or look like this. All those little bites, what we in the scientific trade called arcuate bite-like structures, just to be silly. All of those represent some type of landslide. Submarine landslide, probably. Now, if you look at this one, this is the one this is Minaya, where they've had 6 events in 30 years. This affected that bit of coastline there, the most recent one, and they've had another 5 of those in 30 years. This one, well, it's had a good couple of chunks taken out here, one here, one here, one here, and so on. Multiply that by 30,000, and you're starting to get a sense of the enormity of the problem. We have absolutely no idea how big those are at the moment, and we have absolutely no idea how often or even when they occurred, except for those ones on the Cook Islands there. So no idea. Are we comfortable? But it gets a bit worse. It's got to get worse before it gets better. The landslide cousins, the ones, well, actually not really landslide, but both above and below water. I'm not calling them flank collapses because they're not coming off the side of an atoll or something like that, but they're very similar. Lituya Bay, 1958, is the largest historic tsunami of all time. The water got up to a height, or the tsunami that was generated by it, not the actual wave height, but it actually ran up the land, up to 530 meters above sea level. Yes, that's more than half a kilometer. And that was generated by an incredibly small event, 0.03 cubic kilometers. What's that? 3/300ths of a Hagley Park or something like that. Not very big at all. So that can be pretty devastating. But then let's come back to New Zealand. The Ruatoria slide. This is East Cape. Greetings. This is our continental shelf. This lump there is about the size, slightly smaller, but about the size of Mount Cook. Just that one bit. And this is the slide here. 3,200 Hagley Parks. It happened some time ago, about 120,000 years ago. That's great. How high did the wave get? No idea. No one's ever found the evidence for it because no one's ever looked. How big? No one's ever looked. How often do these occur? No idea. Next page. Other ones, because we haven't quite finished with the things that generate tsunamis yet. We have meteorological tsunamis. They can hurt. They are pressure disturbances that usually move along in front of something horrible. The reason why the Krakatoa tsunami was so big was there was a pressure wave caused by the eruption that moved out away from Krakatoa, and that was largely what was generating that tsunami, as opposed to the actual volcanic eruption itself. We have things called gas hydrates. They're basically big bubbles of gas that sit underneath the seafloor, and every now and again they decide to go, and that can generate a tsunami. Or they can actually cause submarine landslides. It's now thought that gas hydrates blowing off on the edge of the continental shelf up in Norway were responsible for generating an event called the Storegga slide, which is the largest event ever recorded, I think, in the Northern Hemisphere. You find that evidence in Scotland. Hold on, let me think. Find the evidence in Scotland, England, Iceland, Greenland now, Faroe Islands, and all around the North Sea. Big event. Not very pleasant. Can't remember how long ago. I think about 8,000 years, or 6,000, one of the two. Somewhere around there. Those little black dots, incidentally, show you where most of the gas hydrate deposits are that we know about around the world. There's Japan, and there's New Zealand. We have a nice big dot. And then, not to be left out, we have humans, because we do a great job at generating tsunamis. Everyone's heard about the special secret one in the Second World War where we were asked to see if you could generate tsunamis by blowing off various sizes of TNT underwater. I can't remember what it was called, Project something, I've forgotten, but in principle it works, so we could do that if we really wanted to, which is great. Unfortunately, in the case of Halifax, there was a large ship full of TNT in 1917. That blew up, and both the explosion and the tsunami killed an awful lot of people. So we're joining the trend. We're doing a great job. Okay, so improving our knowledge. That was a quick run through of all the nasty sources that we don't really think about too much, and we don't want to, but we don't include them in the model, so don't worry about it. The Pacific is 165 million square kilometers. It's a big place. 22 Pacific Island countries. 20 to 30,000 islands, actually. We don't know. No one's ever really counted. And what you call an island, and scientists get tied up on these things. And then there's all the people who live around the edge of it as well, like the Japanese, the Chileans, the North Americans, us, Australians. Oh, they don't know. Yeah. 85% of all historically documented tsunamis have occurred in the Pacific. So this essentially is the tsunami problem. Don't worry about anywhere else in the world. They get one every now and again. This is where the action's at. The Indian Ocean one, which everyone thinks about and thinks about and thinks about, doesn't happen very much. Much bigger, much more often in the Pacific, which has really got me worried now. So you think how bad the 2004 was. So back to the hazard assessments. Here we have that lovely little diagram again with all these subduction zones firing things in. Well, we know from what we've done we can improve on that. So we can have, that's that asteroid hitting the sea down here at some point, doesn't really matter. These little things are all submarine landslides. I put a few in. I really couldn't be bothered to put in about 100,000. It was just too much like hard work. And these little red circles are volcanoes that we know have blown up and we know have generated tsunamis, some big, some small, not too big a deal. But it's starting to color our understanding of the tsunami hazard a little bit more than just that. We're getting a bit more. So that's what we currently know. We know this already. This is not new work we're doing. Okay, so let's have a little look at New Zealand. What are we missing now? So in 2005, there was a report pumped out, Generalised Assessment of Tsunami Hazard in New Zealand. This is the one for 2,500 year return period. I should point out this is, I believe, looking at subduction zone events only. I should point out, 2,500. So once every 2,500 years, essentially, biggest one you're going to get is in the Chatham Islands, so that's fine. 12 to 14 meters, 2,500 years. Now remember the first slide I showed, which was 42 meters, slightly wrong. We have this disjunct. It exists, this disagreement between what the models show and what geology shows. And remember, geology is still not getting it entirely right either. So both at fault here. But what we have, for example, this is a lovely rock. There's quite a few of them, but I actually like this one quite a lot. That little thing there that the person's pointing to is a hole that was bored into the rock by a little shell that lives on rocks in the sea, and it bored this hole into it. And it's called a gastropod borehole, if anyone's interested. This little nice sort of curvy bit here is what they call a wave cup notch. It's where the sea carves away merrily. You can usually see it at low tide. You look down the coast where the rock, and you see this curvy shape to it. That's where the sea level generally is around about at any one time. So in the 15th century, this clearly marine rock, which is not the same bedrock that it's sitting on, and it's also sitting on top of some old Maori occupation sites as well. So it actually happened around about the 15th century. This sits 60 plus meters above sea level. Now, okay, you could say, well, it wasn't put there by a tsunami. It was put there by what? I don't know, a camel or I don't know what. It couldn't be put there by a storm. Couldn't be put there by a water spout, which is a possibility in that neck of the woods. I'm not going to tell you where it is because I haven't published it yet, and I've had this data for 10 years, but I love showing it. So what I always do is I use its poor cousin up the top end there and say, well, that was 42 meters above sea level. This one's higher. More work needs to be done is the answer to that. But let's have a look at this example, and this is what we knew then, back in 2001, when we were doing this work and that paper came out. We all still know this now, and it's still not included. These are the data, the geological data that the model miraculously matched up with, but this can't happen. This is that event. There are 35 sites, contemporaneous, same age, basically. 35 sites coming all the way from, that's Ahipara there, so this is south of there, all the way around Northland, all the way down here, past Great Barrier, does a great job at protecting Auckland. That's why it's called Great Barrier. And then down into the Bay of Plenty. Now this is based not just upon geological data, and this is where the really important strides are being made in understanding previous events. It's geological data, geomorphological, the shape of the land, not what the land is made up of. Ecological data, archaeological data, even anthropological data. We have a rich history of oral traditions in this country. Yes, it only goes back a few hundred years, but that extends our couple of hundred years of historical record much further. We have to use all of this kind of information. This event goes up to 60 meters above sea level. You notice how I did this. Anything in gold is greater than 21, so it's one of those ones. There you go. That's as far as that one's going. And this occurred somewhere between 1450 and 1480 AD. We managed to fine-tune it to that point. As an example of what we've got here, here we have a Maori, I should do it on this side for a change. Here we have an old oven, and that oven is overlain by a tsunami deposit right here. That site, not surprisingly, was abandoned. Like we would probably do when one came in, we would abandon it as well. And the people who were affected by this quite wisely went inland and uphill, which is something else we're also told to do, but preferably before the event. And here, I don't know how well you can see them, but these, because that funny, what is that thing? Let's see if I can get rid of it. It's been annoying me. Technology is wonderful, isn't it? This here, these are bones. This was a burial, an old Maori burial. These are now exposed at the surface because all of the sediment has been taken away by that particular event and thrown inland with a lot of people. So what are the sources? Because we've got to remember that this is not only New Zealand. Events this size are affecting elsewhere as well. It can't just be us. You know, we're sharing this with other people. And when you look around, this is almost the entire amount of work that's been done on prehistoric tsunamis in the Pacific Islands. It's almost the entire data set that exists. And you'll see, if you look not too carefully, you'll see here's that event there. Oh, that kind of covers the same time period. That's pretty close. That's pretty close. That's pretty close. That could be. That's pretty close. Oh, dear. That was, oh, dear. It gets worse. That covers a lot. And so there's a lot around about that event in the 15th century. And if you sort of look carefully, and I don't move the slide fast enough, you'll find 2,800, 2,900, 2,800. There seems to be something happening a bit earlier too. Oh dear. What on earth could the sources be for these? Let's have a look at our two friends. Kauai, that was the one that blew up in Vanuatu, and our dear friend, the Tonga-Kermadec Trench. Because these are the ones that, well, certainly the Tonga-Kermadec Trench is going to be the big one for us, big problem for us. Fortunately for Christchurch, it may not be that bad. We have other things to worry about down here. So let's have a look, because the reason why we're concerned about tsunamis is not because they're going to hurt a few trees or anything like that. It's because they're going to kill us. It's because they're going to knock over our houses, because they're going to destroy our infrastructure. If we weren't here, we wouldn't really be worried about it. You know, humans, they're a hazard to humans. So these things have a fundamental effect upon people. So we can learn from the Pacific, not necessarily entirely from New Zealand. We can expand our horizons into the South Pacific at least, and we can look at how these things might have affected Polynesians. Because 4,000 years ago, there were no Polynesians at all in the Pacific. The proto-Polynesians, or the trainee Polynesians, were sitting over here in the Bismarck Archipelago, quietly waiting, or just not moving into the Pacific. By 2,800 years ago, Western Polynesia had been created. Polynesians had come down here, Western Polynesia's here, and about 2,800, 2,900 years ago, they got to the Samoan, Tongan archipelago and stopped. Didn't do anything at all, which is quite fascinating because at exactly that time, we have the first event that we've managed to get back 3,000 years. The record undoubtedly extends back further, and there are other events, but this is the first one that affected humans in the Pacific. We have an event 2,800, 2,900 years ago. You can find it as far over as Australia, bless their cotton socks. And you can find it as far north as the Northern Cooks, and you can actually find it perhaps as far away as Vanuatu as well. So it's not too bad, and possibly, yes, it definitely comes down to New Zealand. So that's a reasonably large event, particularly since it's managed to survive 3,000 years in the geological record for us to find it, which is great. We have to remember that Polynesians, seafaring race, culture, living in coastal settlements. You throw in a very, very large tsunami, it does serious damage to your canoes apart from anything else. It obliterates your community. It destroys your shellfish beds, your intertidal shellfish beds, because it picks them all up and throws them inland. It puts salt water over any crops that you might be growing, so it kills those. Generally, it has a fundamental impact upon your culture and your settlements as well. So perhaps that's the reason for the beginning of the long pause. That's why they stopped. The long pause is a big conundrum in Pacific archaeology. They stopped here and nothing happened until about 1100 AD. A little bit of wandering around, a couple of little islands settled, but basically nothing happened. And then suddenly, at the end of the long pause, somewhere between, around about 1100 AD, between that and 1300 AD, pretty much everywhere got settled in the Pacific. Eastern Polynesia was created. All these places filled up nicely. It was a very, very rapid expansion, absolutely lovely place to be. Why then? Nothing to do with tsunamis, but it's fascinating. Absolutely fascinating. Nearly 2,000 years doing nothing and then suddenly bang. I'm not an archaeologist. I work with them and they scratch their heads and wonder what's going on. Maybe it's just time to move. Don't know. Okay. And then there was this phenomenally successful long-distance voyaging communication network set up, trading. So artifacts from New Zealand you can find in the Marquesas, for example. Things from Vanuatu you can find in Pitcairn. Things from Hawaii you can find in summer. It goes on for a wonderful trading going on. Very, very sophisticated stone tool culture as well. These were a very advanced Stone Age culture. Absolutely fantastic. And then the proverbial hits the fan. The second, actually it was the third, I've missed one out deliberately, but the second larger Tonga-Kermadec Trench event occurs, and Kauai happens as well. Both very closely spaced in time there, and those overlapping shaded areas give you an indication of where we found evidence. Doesn't mean that's the extent of it, that's where we found evidence so far. Costs a lot to go to Pacific Islands and work. It's a very expensive thing to do. Instantly, pretty much, within about a decade, there was a collapse, complete and utter failure of the long-distance voyaging system. People were then left on their own. They were left with all the resources they had left to deal with, and they guarded them jealously. They couldn't get all these other tools and things and stuff from everywhere else because all those long-distance voyaging network had broken down. Not surprisingly, because all canoes had been smashed to pieces, which is not very helpful. But also, when a tsunami of that magnitude hits, it preferentially kills two lots of people. It kills the women and children. It usually kills the children, and then the mothers rush in. The mothers are rushing around trying to find the children, and they get killed as well. But it also kills the elderly, who are less capable of looking after themselves. And in Polynesian culture, the elders are the keepers of the knowledge. You lose the knowledge, how do you make that stone tool? You lose the knowledge, how do I make that canoe? I'm not quite sure, you know. And you see a distinct change. In New Zealand, you have the archaic and the classic. Classic stone tools are made by kids in comparison to the archaic. They're very sophisticated. And it's fascinating. You find this throughout Polynesia. Why is this? Oh, and you also get chiefdoms and you get warfare, of course, because people are fighting over resources and increasing isolation. And not surprisingly, it's probably where cannibalism started because it's a good protein source. Probably. Don't know. I'm stepping outside of my milieu there. The significance of this, other than the fact that it was horrible, this happened in the last millennium. It's not a long time ago. Less than 600 years ago this happened. It had predecessor events that we know about, actually 2 of them, in 3,000 years. These are not included in tsunami hazard assessments. That's a worry. And that's as much my fault as it is a modeler. So we need to innovate. I'm getting near the end, folks. We need to innovate. Here's a good example from a place called Siletz Bay in Oregon. On the left is the model of inundation, not including geological data. On the right is the model including the physical evidence from 6 previous, what we call paleo-tsunamis, that occurred over 2,800 years. And that is their model, I think, for a 1 in 500 year event. I could be wrong there. Wow, there's a big difference. Significant difference there. That is the kind of thing we want to see. But the physical evidence is moving on. That particular piece of work was based upon sand. It all comes back to the beginning of the talk. That was based upon sand. And we know from our experience in Japan that the sand, for example, in that case, only went 60% of the distance inland of the total inundation of the tsunami, undercooking the size of the event. We're now moving along significantly. We can use things like geochemistry. We look at the mud to start with, which is great. We can just use geochemistry because salt water leaves behind salt, essentially, in the system. And that can hang around for a long, long time. You can plow it. You can do a whole bunch of things with it. The longest we've gone back finding geochemical evidence, which was in New Zealand, is 6,300 years. So we can find the signal of a tsunami deposit, or tsunami inundation, because it's not really a deposit, 6,300 years ago. That's in northern Hawke's Bay, by the way, for those of you who come from that neck of the woods. There are new techniques now. We produced a paper last year that basically put everything that we have learnt from the work we've done in New Zealand, but also the work in Australia, America, Hawaii, Japan, etc., and a bunch of work that other people have done into this big kind of compendium of a paper which says this is how you identify old tsunamis. We've got to do it this way. Because if we don't do it this way, we're going to undercook the size of these events. And even archaeologists now are getting very good at going back through some of their old records and identifying where tsunamis, where a site was abandoned and it's got a sand layer sitting on top of it. And looking at those again and going, you know what, that could have been a tsunami. We didn't think about it at the time. I'm not saying anything bad about archaeologists because they were doing this work way before. We didn't start doing tsunami work until the early 90s. Almost anywhere in the world, some did it in the 80s. Archaeologists have been in the Pacific for well over 100 years doing work. So they've got a great database which can now be looked back at with these new glasses that we're using. So we must remember that, I suppose, the major failing with these existing tsunami hazard things and the complacency, not only for the science, but also for people who are being told it's not that bad, we're underestimating the hazard because we are limited by our understanding of what's called geophysics, how the things work, how subduction zones work, and how landslides happen, and it's really complicated, and our understanding just cannot get around trying to model those kind of things. We're really limited by our understanding of big. 2004 was a huge wake-up call for the tsunami community. That event shouldn't have happened. And then we had 2009 in the South Pacific. Apparently those type of fault movements shouldn't generate tsunamis, but they did. And then we had 2011, which caught Japan out majorly. That shouldn't have happened, but it did. So we're not doing very well at the moment. We don't get big right. And sadly, we're not using or believing, perhaps is a better way of saying it, all the data that are available to us to use. And here's a classic example. This is a beautiful site. I don't know if anyone... This is Greville Harbour, D'Urville Island, western side of D'Urville Island. In Maori terms, it's called Murfitu. There was a wonderful oral tradition from Murfitu about... there was a woman, picking various vegetables and things, and she picked the wrong thing. It's always the women who are doing the work. And she picked the wrong one, and the god Tangaroa was a wee bit unhappy about that. So he sent in this big taniwha to seek vengeance and utu against the particular community there. And this taniwha, which is called Tapu Reru Utu Utu, came in, and it was in a frenzy. And it was picking people up and throwing them into the dunes and sucking them out to sea. And in its frenzy, a bit of its tail broke off. And it sits out there in D'Urville Harbour as a reminder to the people who live there not to do it again. Interesting. Oh, and this, incidentally, is just a cave painting of a taniwha, sea monster, eating a human. There's a wonderfully rich database of traditional environmental knowledge that we simply don't use enough, and we should do, because it is yet another strand in the information that will tell us how big some of these events can be. So coming back to my dear modelling friends, in theory, theory works well in practice, but in practice, it doesn't. I was going to say something else. The modelling isn't working. We are complacent, and it's not working because sometimes because of the geology, sometimes a whole bunch of reasons. We are complacent if we choose to believe the tsunami hazard assessments that we're told about. That's the first point. In all but the most enlightened exercises of modelling, do you see, even in those ones, even in the best ones, there's still this disjunct between the physical evidence and the modelling, because the modelling's been made to fit with the geology in the most enlightened ones. That's great, but now the geology is moving on, or in, if you want to say. So we need to now go back and revisit again the models and make them bigger. It's a bit of a struggle, but we're getting there. Tsunamis are basically magnitude and frequency. That sounds a bit scientific. The bigger magnitude events don't happen as often. That's really what it's saying. So not surprisingly, the bigger events have occurred in prehistory. We only have a 200-year historic record. It is just simply not enough. So we're kind of stuffed there from that point of view, unless we do more geology. And quite rightly, a little knowledge is most definitely dangerous. More so because a lot of the knowledge we have, which is a bit, not a little, is currently ignored. So we're not even using all the modelling, all the data we should be using. There are major advances being made, and this is absolutely great. Now is the time for where my dear colleagues, the modellers, and myself and the geologists need to seriously get together. We need to work together, because at the moment we've got this kind of complacent attitude of, well, I know best. No, I know best. We need to get together, hold hands, sing songs in tune, and hopefully we will actually come up with much better tsunami hazard assessments in the future. The ones we've got at the moment are fine, but we can do better. If I was marking this, I'd give myself maybe a B- or something like that. We have a lot of work to do. Oh, incidentally, that's an extremely large boulder sitting in the Chatham Islands. Thank you very much indeed. And